Today we're going to talk about uniform circular motion, as well as slightly touching on non-uniform circular motion, and we'll talk about relative motion. So uniform motion, circular motion is when you have some object that is moving in a circle at a constant velocity. So we can describe the position of the object as some radial displacement from the center of the circle, and then an angle. And the velocity will just be tangential to the trajectory, so tangential to the circle. So when we have uniform circular motion, that distance r is constant. The magnitude of the displacement from the center of the circle is constant. It's only the angle that is changing. And since we're going at a constant velocity, the magnitude of that velocity vector is constant. So the direction of the displacement and the direction of the velocity will change as it goes around the circle, but the magnitude of r and v will not change with time. Examples of things, of applications of uniform circular motion. If you understand uniform circular motion, you can work with things like the Earth going around the sun, or the moon, or satellites going around the Earth. If you're swinging a ball on a string, like when you use a slingshot, understanding merry-go-rounds, a spinning car tire is a problem we'll work in a minute. When you swing a golf club, right? Now, when you swing a golf club, the club accelerates, but for a brief moment in time, you can kind of imagine a little piece of the arc being something like uniform circular motion. We'll talk about non-uniform circular motion briefly, which is what you would apply to a golf club. A conical pendulum, a pendulum that's oscillating in a circle. So lots of cool things you can understand if you understand uniform circular motion. So now as my object is moving around the circle, as theta changes by some amount d theta, the path that the object traces out, the length of that path, is just delta s, which is the radius of the circle times delta theta. So that means that the velocity, that's just the derivative of s with respect to time, that's just r times the derivative of theta with respect to time. And we have a special name for the derivative of theta with respect to time. We call it omega. All right, we use the Greek letter omega to represent the derivative of theta with respect to time, and we call it the angular velocity. So the linear velocity, the velocity that something on the edge of that circle is moving, is related to the angular velocity with the equation v equals r omega. Now the period, the time it takes to do one complete circle, that's just the distance, the circumference that you travel when you do one circle, 2 pi r, divided by the velocity, v, but that's also just 2 pi over omega. Now, what direction will the acceleration be if something is undergoing uniform circular motion? Well, in a previous video, we talked about how we can break up acceleration into two components, a component which is parallel to the velocity and a component which is perpendicular to the velocity. The parallel component, we said, doesn't change the direction, but it changes the magnitude of the velocity. The perpendicular component doesn't change the magnitude of the velocity, but it changes the direction. So in this problem, where the velocity's magnitude is not changing, there must not be a parallel component of acceleration. It must all be perpendicular to the velocity. All right, so as we move around the circle, the acceleration is always inward, perpendicular to the velocity. So the acceleration will always be inward, opposite the displacement, right? So the magnitude of, the direction of the acceleration will be in the opposite direction from the displacement. So if I take the acceleration divided by its magnitude, that will equal negative the displacement, the position, divided by its magnitude. Or in other words, a unit vector in the acceleration direction is equal to negative a unit vector in the r direction. So the acceleration will always be to the middle of the circle if we're undergoing uniform circular motion. And the magnitude of the acceleration will be constant, right? There's a symmetry to this problem. If it's equal to one value over here, it must be equal to the same value over here. So we're going to start from a description of the position of the object as a function of time, and then from that we can find the velocity and the acceleration. So what is the position as a function of time for something going in a circle? Well, it's just the radius of the circle times cosine omega t in the x direction plus r times sine omega t in the j hat direction, in the y direction, right? And so initially it'll be in the x direction. Sometime later, cosine will go to 0, sine goes to 1, and it'll be in the y direction, and it'll just trace out a circle. Well, this is not as general as I'd like to be, because this assumes that at time t equals 0, the object is on the positive x-axis. Let's give ourselves some more flexibility by putting a little theta naught in here, right? So that by changing theta naught, we can change the position of the object on the circle at time t equals 0. We also might want to consider an object going the other way, right? So maybe we want to put a minus sign here so that we can make something that goes in the clockwise rather than the counterclockwise direction. But it turns out we don't need to do that. We'll just go with this function right here because I can make it go in the opposite direction simply by changing the sign of omega. Okay, so if r is equal to this, what is the velocity? Or sorry, what's the magnitude of r? Let's look at the magnitude of r first. So to get the magnitude of a vector, I just take the x component squared plus the y component squared and take the square root of that. All right, and the x component is just r cosine and the y component is r sine. But sine squared plus cosine squared is 1, so I just get the square root of r squared, which is r. Good, that's what we wanted. We intended to write down a vector position whose magnitude was the displacement from the origin, the magnitude would always be r, and that worked. So now to find the velocity at any given time, we just take the derivative of the position. So with the x component, we take the derivative and we get, so r is a constant. We take the derivative of cosine, we get negative sine. Using the chain rule, we find that when we do that, we get an extra factor of omega out front. When we do the y component, we get, sine goes to positive cosine. Once again, we get an omega out front. So that is the velocity. The magnitude of the velocity is, once again, if we plug this in and use Pythagorean's theorem, we're just going to find that it's equal to omega r. But remember, we said omega r is just the velocity of the edge of the circle. So, yeah, basically we found that the velocity has a magnitude, which is the velocity, which is r times omega. Okay, but notice I have a minus sign here, and I have cosine becomes sine and sine becomes cosine, so the velocity will be perpendicular to the displacement. You can prove that that's true. I didn't take the time to do this, but remember, if I take the dot product of two orthogonal vectors, I get 0. So if I get 0 when I do a dot product, it means they're orthogonal. If I do, you can try this on your own. Take the dot product of these two and show that velocity is at 90 degrees to the displacement, to the position r. Now to find the acceleration, I just take the derivative of the velocity. Sine goes to cosine, brings out another factor of omega. Cosine goes to minus sine, brings out a factor of omega. So there's the acceleration. Well, the magnitude of the acceleration is, as you're going to see here, if I just plug this into the Pythagorean theorem, I'm going to find that the magnitude is v times omega. But remember, omega is just velocity divided by r. And so the magnitude of the acceleration is a constant, and it's just equal to v squared over r. So, important things to remember about uniform circular motion. The acceleration is inward towards the center of the circle, and the magnitude of the acceleration is just the velocity squared over r. So, once again, we can write our equations this way. R is just r cosine plus r sine in the y direction. V is just negative v sine in the x direction, positive v cosine in the j direction, and acceleration is negative v squared over r cosine in the x direction, negative v squared over r in the sine of omega t plus phi, that should be phi naught, I dropped my naught somewhere, in the y direction. But notice that this is just negative v squared over r squared times r, so the acceleration can be written in terms of r because they are in exactly opposite directions. All right, so one important thing to remember, once again, if I have something moving in uniform circular motion, the magnitude of the acceleration is just v squared over r. So Here's an example problem. The Earth travels around the Sun at a distance of about 150 billion meters. What is the magnitude of the Earth's acceleration caused by the Sun? Well, acceleration is just v squared over r, and velocity is just distance per unit time. So the circumference of the Earth's orbit divided by 1 year, right? And so I can simplify that, and I find it's just r times 2 pi over 1 year squared. Well, 1 year is 365 days. I can multiply that by 1. 24 hours over 1 day is 1, right? And then the days cancel out. Then I'll multiply that by 60 minutes per hour, and the hours cancel out. Then I'll multiply that by 60 seconds per minute, and the minutes cancel out. And I find that 1 year is 3.1536 times 10 to the 7th seconds. So the acceleration is just r 2 pi over t squared. I plug in the radius of the orbit, which is 150 billion meters. I plug in the time for 1 year in seconds, and this comes out to be 5.95 times 10 to the minus 3 meters per second squared. All right, that's significantly smaller than the acceleration due to the Earth's gravity, right? But it's not like a billion times smaller. It seems pretty incredible to me that the acceleration that the Sun causes on anything that is one Earth orbit away from it is reasonably big, considering the fact that the Sun is about 150 billion meters away. Here's another example. A spacecraft consists of a large ring with a radius of 155 meters. The ring rotates about its axis with a constant velocity to mimic the feeling of gravity for those standing on the inside of the ring. How fast does the edge of the ring need to be moving to simulate Earth's gravity? All right, well, we know that the acceleration of something standing on the ring is just v squared over r, but we want that acceleration to simulate gravity. We want it to be equal to g. So now I just solve this for the velocity. I multiply both sides by r, take the square root, there's the velocity. I plug in my numbers, and I find that the velocity needs to be about 39 meters per second. All right? Okay, now let's talk a little bit about non-uniform circular motion. So imagine I have something moving in a circle, but the velocity is not constant. So remember, the component of acceleration, which is perpendicular to the velocity, changes direction, but not the magnitude of the velocity. If I want to go in a circle with a velocity that's changing, I have to add a component of acceleration which is perpendicular to the displacement, such that it's parallel to the velocity. I need a component which is parallel to the velocity to change the magnitude of the velocity. So I add those two together, and I get then now an acceleration which is not pointing towards the center of the circle. All right, but let's just think of the acceleration in terms of the components. The radial component of acceleration, the one that points inward towards the center of the circle, is just v squared over r. That's what it needs to be to turn the path and make a circle. But now, if the velocity is not constant in time, the radial acceleration may not be constant in time. Well, it won't be constant in time anymore. All right? Then the tangential component of acceleration is what causes the change of the magnitude of the velocity. So it's just the derivative of the magnitude of the velocity with respect to time. So imagine this. I have a merry-go-round that has a radius of 11.5 meters. At time t equals 0, it is not moving. 30 seconds later, it is spinning at 1 revolution every 3.11 seconds. Assuming that the velocity of the edge of the merry-go-round increased at a constant rate during that 30 seconds, what was the radial and tangential acceleration as a function of time for a banana sitting on the outer edge of the merry-go-round? Well, the tangential acceleration is just the change in velocity per unit time. And this is going to be constant because in the problem we said that the velocity at the edge of the ring, at the edge of the merry-go-round, is going to increase linearly with time. So that means that the tangential acceleration is just how fast it's going after 30 seconds divided by 30 seconds, right? So t30 is just how my variable where I'm going to plug the time it took to accelerate up, which is 30 seconds. Well, what is the velocity after 30 seconds? It's just the circumference divided by the period, the time it takes to do one circle after it's accelerated for 30 seconds. And here, that time is 3.11 seconds, right? The problem said after 30 seconds of accelerating, it was rotating at a rate of 1 rotation every 3.11 seconds. So that means the acceleration, the tangential component of acceleration, is 2 pi r divided by t30 times little t30. We can just plug in the numbers now, and we find that the tangential component of acceleration is 0.774 meters per second squared, and it's not changing with time. Now, what is the radial component of acceleration? Well, the radial component of acceleration is just v squared over r. But now v is not a constant. V is v naught plus at, right? The velocity is changing linearly with time. Of course, at time t equals 0, there is no velocity for the edge of the merry-go-round, so v naught is 0. That means that the radial component of acceleration is just v squared over r, and v is just the tangential acceleration times time, which is 2 pi rt over t30, little t30, right? So we plug that in. I'm going to pull out the r squared and cancel one of the r's with the 1 over r. I'm also going to pull out the t squared. And so there's the formula for the radial acceleration, the component of acceleration which is inward towards the center of the circle. All right, then I'm going to plug in numbers. I calculate this, and I find that the radial acceleration, the component of acceleration inward towards the center of the circle, is 0.0522 meters per second to the fourth times time squared. Now, we're going to talk about relative motion. So imagine an F-16 is flying along, and while it's flying, an F-15 flies past it. Zoom. All right, so if I know the velocity of the F-16 relative to the ground, and I know the velocity of the F-15 relative to the ground, the velocity of the F-15 in the reference frame of the F-16 is just going to be the velocity of the F-15 minus the velocity of the F-16. Right? So because the F-16 is moving, from the F-16's perspective, the F-15 is not moving as fast as it is from the perspective of the Earth. Now, if the pilot of the F-16 measured the relative velocity of the F-15, they could find the velocity of the F-15 relative to the Earth simply by taking the velocity of the F-15 relative to the F-16 plus the velocity of the F-16 relative to the Earth, right? So the velocity of the F-15 relative to some reference frame is just the velocity in some other reference frame plus the velocity of that reference frame, if that makes sense. So, for example, you're driving a red Honda South on I-15 at a speed of 78.2 miles per hour. You pass a blue VW Bug going in the opposite direction whose driver is the spitting image of Paul McCartney. In your reference frame, the Bug is going 165.3 miles per hour. What is the Bug's speed as measured by someone standing on the side of the road? Well, your velocity is negative 78.2 miles per hour. Negative because I'm going to let north be positive, and you're moving south. All right? The velocity of the fake Paul McCartney relative to you is 165.3 miles per hour in the plus direction, going north. But the velocity, the relative velocity, the velocity of fake Paul McCartney relative to you is the velocity of the fake Paul McCartney in the Earth reference frame minus your velocity in the Earth reference frame. That means that the velocity of the fake Paul McCartney in the Earth reference frame is the velocity of the fake Paul McCartney in your reference frame plus the velocity of you relative to the Earth reference frame. So the velocity of fake Paul in the Earth reference frame is the velocity of fake Paul in some other reference frame plus the velocity of that reference frame. So the velocity in your reference frame is 165.3, but your velocity is negative 78.2 miles per hour. We add them together, and we find that the velocity of the fake Paul McCartney in the Earth reference frame is 87.1 miles per hour going in the plus direction, going north. Here's another example. Imagine that a car is traveling at 65 miles per hour. How fast is the top of one of its tires moving? This combines reference frames and uniform circular motion. So let's start in the reference frame of the car. In the reference frame of the car, the center of the wheel is not moving, but the edge of the wheel is moving at a velocity which is the angular velocity times r, omega times r. All right? The top of the the top of the wheel is moving forward with that velocity. The bottom of the tire is moving in the other direction, backwards. Now we're going to transform into the earth reference frame. To transform into the earth reference frame, I need to change the velocity such that the bottom of the wheel is not moving, right? Because in the earth reference frame, the bottom of the wheel, it momentarily comes into contact with the road, and it's not sliding on the road, so that means that the bottom of the wheel is moving at 0 miles per hour. So to transform such that the bottom of the wheel is moving at 0 miles per hour, I had to transform into a reference frame that adds omega r to all of my velocities, which means that the top of the car's wheel is traveling now at 2 omega r. Well, I transformed into a frame by changing velocities by omega r. Well, I'm really transforming into a frame in which the car is moving at some velocity. So omega r must be the velocity of the car. So the top of the tire must be moving at twice the velocity of the car, or 130 miles per hour. All right, hope you enjoyed today's lecture.